In mathematics, the look and say sequence is the sequence of integers beginning as follows: 1, 11, 21, 12, 11, 111,221, 312,211, 13,112,221, 1,113,213,211. To generate a member of the sequence from the previous member, read off the digits of the previous member, counting the number of digits in groups of the same digit. For example, 1 is read off as 1 1, or 11. 11 is read off as 2 1s, or 21. 21 is read off as 1 2, then 1 1, or 12 11. 12 11 is read off as 1 1, then 1 2, then 2 1s, or 111,221. 111,221 is read off as 3 1s, then 2 2s, then 1 1, or 312,211. The look and say sequence was introduced and analyzed by John Conway. The idea of the look and say sequence is similar to that of run-length encoding. If we start with any digit d from 0 to 9, then d will remain indefinitely as the last digit of the sequence. For d different from 1, the sequence starts as follows: D, 1D, 111D, 311D, 13211D, 11131221D, 3113112211D. Ilan Vardy has called this sequence, starting with D equals 3, the Conway sequence. Basic properties. Growth: the sequence grows indefinitely. In fact, any variant defined by starting with a different integer seed number will also grow indefinitely, except for the degenerate sequence. 22, 22, 22, 22, digits presence limitation: no digits other than 1, 2, and 3 appear in the sequence, unless the seed number contains such a digit or a run of more than 3 of the same digit. Cosmological decay: Conway's cosmological theorem. There are 92 elements containing the digits 1, 2, and 3 only, which John Conway named after the natural chemical elements. There are also 2 transuranic elements for each digit other than 1, 2, and 3. Growth in length: the terms eventually grow in length by about 30% per generation. In particular, if lane denotes the number of digits of the nth member of the sequence, then the limit of the ratio exists and is given by where lambda equals 1.3035772690034, is an algebraic number of degree 71. This fact was proven by Conway, and the constant lambda is known as Conway's constant. The same result also holds for every variant of the sequence starting with any seed other than 22. Polynomial returning Conway's constant. Conway's constant is the unique positive real root of the following polynomial. Popularization. The look and say sequence is also popularly known as the Morris number sequence, after cryptographer Robert Morris. And the puzzle, what is the next number in the sequence 1, 11, 21, 12, 11, 111,221, is sometimes referred to as the cuckoo's egg. From a description of Morris in Clifford Stoll's book The Cuckoo's Egg. Variations. There are many possible variations on the rule used to generate the look and say sequence. For example, to form the p-pattern, one reads the previous term and counts all instances of each digit, listed in order of their first appearance, not just those occurring in a consecutive block. Thus, beginning with the seed 1, the p-pattern precedes 1, 11, 21, 12, 11, 3112, 132,112, 311,322, etc. This version of the p-pattern eventually forms a cycle with the two terms 23,322,114 and 32,232,114. Other versions of the p-pattern are also possible. For example, instead of reading the digits as they first appear, one could read them in ascending order instead. In this case, the term following 21 would be 1112 and the term following 3112 would be 211,213. These sequences differ in several notable ways from the look-and-say sequence. Notably, unlike the Conway sequences, a given term of the p-pattern does not uniquely define the preceding term. Moreover, for any seed the p-pattern produces terms of bounded length. This bound will not typically exceed 2 radix plus 2 digits and may only exceed 3 radix digits in length for degenerate long initial seeds. For these maximum bounded cases, individual elements of the sequence take the form A0, B1, C2, D3, E4, F5, G6, H7, I8, J9 for decimal, where the letters here are placeholders for the digit counts from the preceding element of the sequence. Given that this sequence is infinite and the length is bounded, it must eventually repeat due to the pigeonhole principle. As a consequence, these sequences are always eventually periodic.